How we do on these two guys? A, simple hydration of an alkene with aqueous acid, water and H+. We're going to make cation, left or right? Right, you get a carbocation, and it's actually formed because mechanism, we have H+, these electrons come here, you get boom, 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 boom. Carbocation here, there's a new H here, right? Okay, is that actually formed? Yeah. Whenever you attack an H+, the H doesn't have a lone pair, it can't back bond. Okay? Whenever we attack H+, we always got a carbocation. Now it's prone to rearranging. Is this going to rearrange? No, it's tertiary. It's not going to want to rearrange. Water attacks. These electrons add here. Then you'll lose a proton if you do a full mechanism and you get that structure there. Look good? Hydroboration oxidation, what is that? Atypical hydration? Antimocarbonic hydration. Cation would be on right or left? Cation would be on left, but this is atypical. You actually get where the kind of the nucleophile ends up on the other carbon. Like water ends up over here through this two-step process. There's your product. Okay, you can work it out. Whatever prompts you have in your mind to work it out. Okay. Two types of questions in organic chemistry with synthesis. Predict the product, these two. Then you have mechanism questions, shown at the bottom. Mechanism, you'll have a product shown. You have to show the stepwise. That doesn't mean you shouldn't think mechanistically here. Whatever works for you here. Mechanistically, etc., etc. So prompting. Okay. How we do on this? Over here, we're going to get a chloronium ion, and then water comes in and attacks over here. More substituted, kicks it off. The water, the OH and the chlorine are going to be trans because of this backside attack, kick it off. OH, chlorine trans, this is the product on the end. How do we do? Which one would be best? I think it would be this one here. This is going to give a product with the bromine here, and it's not going to want to rearrange. Here, where are you going to make cation? Well, it's tertiary either place, so it's not going to be selective. Not going to be selective, but this one here, top or bottom? Top. It's going to be selective for making cation there because it's tertiary, and then that's where the bromine bonds. That's going to be a better starting material to get a better yield of that product. Which one doesn't have a stereoisomer? The second one here. That's Z, that's E, that's E. If you try to do Z or E here, you'll have trouble. Because you can't do it. How do we do on that one? Mechanism, alkene gets protonated. Carbocation here. If this OH attacks here, it would be a 7-membered ring. We need to make a 6-membered ring. So 1, 2, 3, 4, 5, 6. OH needs to bond here. Hydride shift would give a tertiary cation. Then the internal nucleophile can attack. We get the ring. Then we remove the proton to get a final product. You could use bisulfate or you could use water because it's an aqueous acid. How does that look? How we do? Questions about any of those? Glad?
On the mechanism, would it be possible that the H is eliminated first before the bond is made?
No, you want to take this H off here?
Yeah.
That's not acidic. You need a pretty strong base to do this. We're under acidic conditions. The only time you're going to take off an H is when the oxygen is positive, no neutral, as opposed to taking it off here and going negative. And as we move forward and do more mechanisms, when you're under acidic conditions, you never want to have any anions No negatives. Other than the conjugate base of your acid. That can be negative. But none of your organic intermediates are going to be negative under acidic conditions. Okay, this will be posted upstairs. Let's see how you're doing. Let's look at the hydrogenation. I think we left something off at the end. And then we'll be looking at stereochemistry. So hydrogenation, the two H's come from the metal. They come in cis or syn addition. That's why this product here is cis. Hydrogenation is an exothermic reaction because we're making two sigma bonds. Let's look at this over here. With hydrogenation reactions, you often talk about a heat of a hydrogenation. Heat of hydrogenation, H of H. This is the amount of heat that's given off when you do the reaction. It's exothermic. Now, if you quote this, this shows here 3 different alkenes. They're all being hydrogenated to the same alkane. They're all going to the same spot. But these 3 alkanes have different stabilities at the beginning. This one's least stable, this one's most stable. Why? Alkene stability is based on substitution. This is now this is condensed. You have to kind of see the bonding here. It's partially condensed. How many carbon substituents on this alkene? 1. Okay, it's condensed. You got to draw. This has 2 substituents. This has 3. More carbon substituents, more stable, right? Okay, so that's why it's shown low. Now they all go to the same place. You need to make sure you see that, because when you add 2 H's here, here, or here, you get the same thing. Which one gives off the most heat, though, when it's hydrogenated? This one, the least stable, because it sits higher. It comes down here. It gives off this much. This gives off less. That gives off even less. The amount of heat that's giving off is called a heat of hydrogenation. Now, the heat of hydrogenation is different from quoting the delta H. Which alkene has the highest heat of hydrogenation? This one. Highest amount of heat given off. Now, if you say which one has the highest delta H, well, then that gets a little bit, well, you're dealing with negative numbers. That one actually has the highest delta H because negative 26 is a higher number than negative 30. So you can get confused. H of H is different from delta H. H of H is a positive number, it's the amount of heat given off. Where the delta H would be a more negative number. Make sure you understand what H of H means. Which alkene would have a higher heat of hydrogenation, left or right? When you hydrogenate these, they both give butane. Which one would have the highest heat of hydrogenation? One on the right. Because it's less stable. It sits at a higher energy. When it comes down to butane, it gives off the most energy. Hydrogenation would be most exothermic for this one. While we're here, we can look at a couple of miscellaneous questions. One of these alkenes reacts with HBr 100,000 times faster than the other. Which alkene is going to react fastest with HBr? Well, there's a little bit of apples to oranges here, but it's hopefully we can get it. Which one's going to react faster? Why the one on the right?
One on nine because it's less stable.
Which reacts faster with HBr? What's the rate determining step for this reaction? Formation of the carbocation. Which one's going to form a carbocation easier? Because we're talking about faster, you need to look at the rate determining step. That's the one that influences the rate. Which one's going to form a carbocation? If you made carbocation here, what type would it be? Primary, secondary, tertiary?
Tertiary.
Tertiary. How about here? A secondary. Tertiary carbocation is going to be much easier to form. This one's going to react faster because you're going to get that tertiary carbocation. It's going to be quite stable, and thus the transition state leading to it. Another miscellaneous question. Now there's a little bit of apples to orange comparison up there. Somebody could make an argument, well, what about this? And I'd say, no, you're onto something. How about down here, though? This is another type of question. Both of these reactions get the same product. You need to make sure you see that. Which reaction would be faster? Oh, how could we, what kind of argument can we make here? Same product, which would be faster? What type of cation is the top we're going to make? What type of cation is the bottom we're going to make? Yes, it's actually the same exact cation. So could that be the answer? Or do we need to look for some other argument?
Number of substituents.
Please be looking at this and think about it. Reaction coordinate diagrams, rate determining step. What could be your argument? You're a lawyer. You've got to solve the case. What information, what aspect of the reaction can you look at and say, aha, this is going to be where the difference is? Please look at that one. Hydrogenation, very important reaction. Just some examples. There's other examples of other reactions. This is a synthesis of the drug Propecia. What are they doing? They're going from 43 to 44. They're hydrogenating this alkene right here with hydrogen. They're using platinum oxide, which with hydrogen becomes platinum metal. And they add two H's here. One of them they drew in. There's another new one here. The reason they drew it in is because that carbon is chiral, and we need to illustrate some stereochemistry, potentially. There's an example of a hydrogenation in the synthesis of Propecia. There's also hydrogenations in the body. Here are your hormones. You learn all these in biochemistry. Here's testosterone. This here is DHT. What's the difference? The alkene is reduced. Hydrogenated. Reduced. When we say that's reduced, the only thing we can't be talking about is hydrogenated. Now it's the alkane. H here, H here. Does this name make sense? Dihydrotestosterone? 2 hydrogen testosterone? 2 H's have been added. Now your body doesn't use hydrogen gas and like palladium. Your body uses like enzymes. This is called 5-alpha reductase. It's an enzyme that does this reduction. Now DHT can cause problems because it leads to hair loss and it also leads to prostate problems. Both of these in male species. Drugs that are used to treat these two things act by inhibiting this enzyme. If you inhibit this enzyme, testosterone is not converted to DHT, and DHT thus cannot cause problems. So understanding the chemistry, then we can say, hey, can we stop this chemistry? Well, usually you target an enzyme to the drug. So that's an example of the hydrogenation or alkene reduction, both synthetically and in the body biochemistry. Okay, we finished up alkene reactions, but you certainly need to be working with them, including stereochemistry. We're ready to begin stereochemistry. We have a yellow handout and then the white packet. Stereochemistry warm-up. Back of the white. So, stereochemistry, hugely important. Hugely important. Just like the difference in your hand ability is very important. Right versus left hand. Here's an example of the importance of stereochemistry. If you look at cellulose versus starch, it's a polymeric saccharide. So these sugar rings just linked polymerically. What's the difference in the two? One little bit of stereochemistry. In cellulose, this is actually a chair conformation. Got an oxygen. In cellulose, the bonds of the oxygen is equatorial. In starch, it's axial. These have the same connectivity. The oxygen's connected to that carbon. Same connectivity. They just differ in the orientation and projection off of that carbon. They're just stereoisomers. But it's hugely important because our body can digest starch, but we can't digest cellulose. If we could eat trees and we would not have any food shortage. Stereochemistry is very important. Here is a flowchart for our isomers. Of course, isomers have the same formula. Two different types of isomers. We've discussed these before. Stereoisomers. There's two different types of stereoisomers, enantiomers and diastereomers. We'll be looking at some of these handwritten terms. Just make sure you know that chart's there and it can be useful. Another example of stereochemistry being important, a drug called Thalidomide, which was given back in the late 50s, early 1960s, largely in Europe, to pregnant women for morning sickness. Unfortunately, there was some bad science, and in research it was good, but when they started manufacturing it, they gave the wrong stereoisomer. It turns out the wrong stereoisomer actually led to birth defects. It led to babies being born with no arms. They were called thalidomide babies. And actually, an American nurse sort of figured out what was going on here, and President Kennedy awarded her some type of a medal or something. But we can mention more about this. That's just stereochemistry. One enantiomer was safe and useful. The other one was very toxic, a teratogen. Okay, let's look at stereochemistry. Yellow outlines. The first thing is chirality. I give you a paragraph about my definition of chirality. Basically, it's also called handedness. Your hands are chiral. Chiral means the mirror image is different. If this looks in the mirror, what will it see? It'll see that. Okay? Those are mirror images. Go hold your hand up. You'll have a hand looking back at you like this. Okay? But are they the same or different? Well, they're different. Because only this one will fit into the right-hand glove. I still can't make this one fit nicely. They're different. That's chiral, mirror images that are different. They have the same connectivity. Thumb connected to a pointing finger. Thumb connected to a pointing finger. They're just mirroring the way they're arranged. In terms of chemical world, let's look at the two different hands or enantiomers of 1-bromo, 1-chloroethane, where the little space is. 1-bromo, 1-chloroethane. Here's ethane. Is that 1-bromo, 1-chloroethane? 2 carbons, ethane. If that's the one position, what do we have? 1-bromo, 1-chloroethane. There's also an H here. But this carbon here is chiral. So there's the compound. Let's look at its mirror image. Well, pretend this looks in the mirror. Pretend that's a mirror here. What would it see? Okay. Do those look like they're mirroring each other? I think the answer is yes. Even with my suspect drawing, those are mirroring each other. Okay? All right. So you got to be able to recognize that. Do we have these two? Let's see here. Black alkyl straight up. H small here. Bromine blue coming towards you. Chlorine green going back. So that's supposed to be that on the board. Okay? Now, this is supposed to be this one. Carbon up, H, bromine blue coming forward, chlorine green going back. That's supposed to be that one. So here are the two on the board. Can we show them mirroring in my hand? Well, let's turn this up. How about that? The H is pointing towards each other. Are those mirroring? This looked in the mirror, would it see this looking back? Yes. So here we go. They have the same connectivity. It's a carbon with an H, a methyl, and 2 halogens. Same connectivity, but are they the same? Well, they are mirror images. Are they the same? If they were the same, we'd be able to stack them on each other. That's called superimpose. Well, that is, will everything line up? The green and black line up. You see? Well, look, the blues don't line up. Okay? Now, if I disconnect and put it here, now they're the same. You see how everything just stacks on each other and lines up? Okay? But how we had it, if I go back to how we had it, they will not. There's no way to make all groups line up. The green will not line up. So what do we have here? We have mirror images. Mirror images. But they're not the same. These are called enantiomers, just like your hands. These are called enantiomers. Okay. Now, what do we want to call the two? How do we want to distinguish them? Well, they have the same exact name. Usually we put some type of stereochemical descriptor in the front. We call these right and left. In the chemical world, though, we use a couple of different terms. If we're talking about an individual carbon, we use R or S. Okay? We need to make a change, but it's going to be easy. It's going to be easy. I don't have to do this. Change that to H. You can just mark it out and change it to H. Change this one to chlorine. First off, does everybody agree that they still are mirroring? Yeah. They're still mirroring. The reason I do this is because there's different ways to do what I'm about to do, but what we had up there would be the hard way, or the more difficult way. Let's start with the easier way. That's why I had to make this change. Hopefully it's pretty simple. Okay, what do we call these? These are right and left. What do we call the chemical world? We do RS. RS is where you assign the configuration around the carbon. This comes from having different configurations around the carbon, and we call this carbon chiral. Let's define chiral carbon. It's a tetrahedral carbon with 4 different groups. And that's really not the broadest definition. That's a little bit sort of narrowed down. That's sort of a good working definition. Why are these chiral? The reason it's chiral is because the molecule itself has no plane of symmetry. And the reason the molecule itself has no plane of symmetry is because at this carbon, there's 4 different groups attached. For example, if both of these were blue, this molecule is actually not chiral. That's because it has a plane of symmetry. The presence of a chiral carbon with 4 different groups gives this asymmetry, and that's why they're important to identify. Okay, how can we name these 2 different compounds? R and S terminology. What you do is you give priority to every group, every atom attached to the chiral carbon. And the priority is given by atomic number, just like when you do E and Z nomenclature. What's the highest priority group attached to this carbon? It'll be bromine. What's the next highest group? Chlorine. What's the next? Carbon, 3. And then the H would be your lowest priority group. You put those on your paper, and then you look. When you go from 1, 2, 3, are we going clockwise or counterclockwise? Counterclockwise. Counterclockwise is called the S configuration. Now, the low priority group is in the back. That's important. Because you say, with the low priority group in the back, is it clockwise or counterclockwise? Now, the low priority group could be forward, or it could also be in the plane, which is where I had it originally. As we move forward, we'll see how to deal with that. With low priority group in the back, it's counterclockwise S. Okay, what's priorities here? 1, 2, 3, 4. Where's the low priority group? In the back. With it in the back, is it clockwise or counterclockwise? Clockwise, that is the R configuration at the chiral carbon. So now this one can be called R. A lot of times you put the parentheses. What is this? 1 bromo, 1 chloro. The name's written. Ethane? Is that right? And this one would be called what? That would be called S. They just have different stereochemical descriptors. These are enantiomers. Mirror images that are different. Enantiomers of 1,1-dibromoethane. That's what I was trying to show. Let's show it again. Okay, I'm just going to erase here. I know that's difficult, perhaps with your paper. Dibromo, 2 bromines. Okay, are those mirror images? That looks in the mirror, will it see the other thing? Yes. Everything's got a mirror image. Except the vampire, right? Just because it has a mirror image, that doesn't mean anything to us. The question is, are these the same or not? Previous example, they were not. Or are these the same? Let's look at them. If this looks into the mirror, the H is straight up. It sees that. Does everybody agree that if they look in the mirror, these are mirroring? Okay. Same or different? What do? Try to superimpose them. Okay. The blues line up, but, or do they? Look at there. See how they line up? They superimpose. They're the same thing. You cannot tell them apart. Mirror images that are the same thing. This compound is not chiral. This compound is called achiral. Mirror image is the same thing. So how many different compounds are on the board? That's just the same compound. Or in the previous case, we had 2 enantiomers. Okay? Well, why are these the same and the previous ones different? It has to do with symmetry. See, when there's 2 bromines, the molecule, single molecule, you can cut right through. It has a plane of symmetry right through it. And if something has a plane of symmetry, its mirror image is going to be the same thing. You see, this is no longer an asymmetric carbon because it doesn't have 4 different things attached. That's a symmetrical carbon. It's not a chiral asymmetric carbon. With the green up here, the compound no longer has a plane of symmetry. You cannot cut right through it. And here we go, take home. Later on we'll play Where's Waldo. Right now we're playing Where's the plane of symmetry. Where's the plane of symmetry? There is none. That tells us that the mirror image is going to be different, thus the compound is chiral. Okay? Is this object chiral or not? What do you want to do? You want to look for what? Plane of symmetry. Do you see a plane of symmetry? Sure, you can cut right through this clip and have half on one side, half on the other. There's a plane of symmetry right through it. Okay? If this looks in the mirror, will it see that looking back at it? Yeah. Everything's got a mirror image. Okay, same or different? It's the same. How do we know it's the same? Because we found Waldo. We found the plane of symmetry. We know that the mirror image is going to be the same. Does your Anna have a plane of symmetry? I cut right through here. I got thumb on one side, thumb on the other. What about like this? Can I slice right through there? Actually, no, because then I'll have a palm on one side, top of the hand on the other. If your hand doesn't have a plane of symmetry, that tells you that the mirror image is going to be different. Later on, we'll look for planes of symmetry. Okay, enantiomers have identical physical properties. I mean, they have the same connectivity, and they actually have very similar projection. They're just mirrored. Have the same melting point, boiling point, dipole moment, density, etc. What do they differ? Well, number one is that it's kind of a quirk of nature, but they differ in how they rotate polarized light. And this is very important, very useful. One enantiomer, like the original two, one enantiomer will rotate polarized light one way, and one enantiomer will rotate it the other way. It's kind of a quirk of nature. But it actually is how, because when the light comes and it interacts with the molecule, one enantiomer kind of does this way. Okay? Like if light came in here, let me some light, and if the thumb kind of influenced it, the thumb would make the light go this way. But thumb me light here. Well, the thumb makes it go this way. So you have the interaction makes the light. But it's very useful. You can do polarimetry, and that's what we'll be doing in lab this week. By the way, I've got lab reports to return back. We'll do that. Number two, they interact with chiral objects differently. Please read that. We'll make a note of that. Let's see if we can do enantiomers of 2-butanol. At least get you going on this. And then please look ahead at optical activity. 2-butanol. Boom, boom, boom. That's a butane with an OH on the 2 carbon. Here. That's 2-butanol. Do you have any chiral carbons? Let's see, what's a chiral carbon? Yeah, it's chiral. Carbon with 4 different butanes attached, tetramutual carbon. Okay, here's what I want you to do. I want you to determine if it's RS and show the enantiomer. Now I'll give you the rotation. The S and the R rotate at 13.5, but one is positive and one is negative. Positive means to the right, negative means to the left. Please do that. Please do this. We'll pick up, please be reading about optical activity. Guys, the Friday lab reports, maybe on Wednesday I'll make some comments about these lab reports. Somebody please close that.